In the previous examples, we did all our calculations based on one reactant, assuming that all the amount of that reactant will get consumed before the reaction is complete. This is not always the case. When you do a reaction, you usually mix two different substances as reactants to form new products. The amount of these two different substances are gonna be different, so they will affect how far the reaction will go. The one that will get consumed first is gonna limit the reaction and it's gonna stop it when it gets consumed. That one is called a limiting reagent. It's the one that is first to be completely consumed, or the one that exists in short supply. So once it gets consumed, again, is going to limit the reaction or stop the reaction. The other one that is in excess is called an excess reagent. Once the other reactant is consumed, the excess reagent is going to remain in excess. So let's consider making a sandwich. You have two components. You have the toast and you have cheese slices. For the equation that describes making a sandwich is mixing two toast with one slice of cheese to make one sandwich. So if you start with 6 toast in combination with 2 cheese, how many sandwiches you will be able to make? You have to follow the ratio in the equation that describes the process, which is mixing each one of the cheese with 2 toast. We have 2 cheese that is going to consume 4 toast and is going to leave 2 more toast behind. So in this case, the number of sandwiches that you were able to make was limited by the amount of cheese slices. You were only able to make 2 sandwiches because you have only 2 cheese slices. So cheese slices are the limiting reagents here. After the reaction is complete, you were left with an excess amount of toast. So toast is the excess reagent in this case. Similarly, in chemistry, you react nitrogen with hydrogen to form ammonia. It goes by this balanced equation right here. So if we have a mixture shown in this container right here, if we try to apply the equations that describes a reaction, we'll see that each one of the nitrogen molecules is going to react with 3 hydrogen molecules, as the equation says. So consuming all the hydrogen molecules is going to consume only 3 nitrogen molecules and it's going to leave 2 nitrogen molecules behind. So now the reactant that was in short or got consumed first is hydrogen. The reactant that remained in excess after the reaction is complete is nitrogen. So hydrogen is the limiting reagent. Nitrogen is the excess reagent. Just one more thing here that is really important. It's not comparing the absolute number between the two substances. Like for example, in this example right here, we actually started with 5 nitrogen molecules and mixed those with 9 hydrogen molecules. You don't just compare 5 to 9 and take the smaller number, which is 5 for nitrogen, and decide that this is the limiting reagent. You have to take the mole ratio of the reaction into account, because for each nitrogen molecule, you need 3 hydrogen molecules. So comparing nitrogen to hydrogen in this reaction, in order to consume the 5 molecules that we have in the mixture, we should have had 15 molecules of hydrogen, which is apparently we have much less than that. If you want to compare it the other way around, consuming all the 9 molecules of hydrogen that we have would only require 3 molecules of nitrogen, which is much less than what we already have. So what will get consumed first is the 9 molecules of hydrogen. and that's why hydrogen is the limiting reagent. Limiting reagent or limiting reactant is going to limit the reaction. So it's going to limit the amount of products that can be formed. So we have to make this comparison between the number of moles of reactant A with the number of moles of reactant C to decide which one of them is short in supply. And that one is going to determine how much or how many moles of the product B is going to get formed. So in this type of calculation, the first step is going to be first determining the limiting reagent or reactant. It's the same thing. And then second step is going to be using moles of limiting reactant to calculate moles product that will form. Combining the two types of calculations, limiting reagent calculation with gram to mole calculation, we will have to convert grams to moles first for both of the reactants, compare moles to determine which one is the limiting reactant, then use the moles of the limiting reactant to calculate moles of the product from the mole to mole ratio of the balance equation, and then use the molar mass of the product here to convert moles to grams. So when you react that number of grams of ammonia with this number of grams of carbon dioxide to make urea according to this equation, how many grams of the product would form and how much of the excess reagent will remain. So the first step is going to be determining which one of these two substances is the limiting reagent by comparing number of moles of each. But we don't have moles, so a pre-step to that is going to be converting grams of each one of them to moles of each one of them. So we convert grams to moles, compare moles to find out which one is the limiting reagent, then use moles of the limiting reagent to determine moles or grams of the urea that will form, which will answer our first part of the question, and then subtract the grams of the excess reagent calculated according to the amount of limiting reagent from the initial grams of that excess reagent. Let's see how that works. So the first step is determining limiting reagent. So we have 637.2 grams of ammonia. Want to convert this to moles using the molar mass of ammonia. Molar mass of ammonia is going to be 14 from nitrogen plus 3 times 1 from the 3 hydrogens. So it's going to be 17 grams of ammonia per 1 mole of ammonia, which is gonna give us a number of moles in 637.2 grams of ammonia, which is gonna be 37.48 moles of ammonia. We repeat the same thing for carbon dioxide, starting from the grams of carbon dioxide, 1142 grams of carbon dioxide. Want to convert them to moles. We know that 1 mole of carbon dioxide has the mass of 44 grams of carbon dioxide. So we get the moles of carbon dioxide in that initial number of grams, which is going to be 25.9 moles of carbon dioxide. Compare these two number of moles to find out which one is the limiting reagent. Again, don't fall to the mistake of just comparing the numbers in an absolute fashion. Don't take the smallest number no matter what. You have to take into account the mole ratio of the equation, which is 2 to 1. In other words, if you compare carbon dioxide with ammonia, we have 25.9 moles of carbon dioxide in our equation, and we have 37.5 moles of ammonia in this reaction. If the 25.9 moles of carbon dioxide would have been to be completely consumed, we should have had 51.8 moles of ammonia to completely consume this, which is apparently we don't have, right? So ammonia is less than what is needed to completely consume carbon dioxide. Ammonia is the limiting reagent. One other way to make this comparison, if you were to consume all the 37.5 moles of ammonia that we have in the mixture, it actually only needs 18.75 moles of carbon dioxide, which is much less than what we actually have. So consuming all the amount of ammonia is going to consume some of the carbon dioxide and leave excess carbon dioxide behind. So ammonia here is a limiting reagent that will get consumed first. And once it gets consumed, the reaction is going to stop, which means it's going to determine how much product can be formed in this case, which is going to be our next step, calculating how many grams of the product formed using the number of moles of ammonia. So we'll take the moles of ammonia and then convert them to the moles of urea that will form using the mole to mole ratio from the equation. 2 moles of ammonia would form only 1 mole of urea. So the ratio is 2 moles ammonia forming 1 mole urea. So the number of moles of urea that will form is going to be 18.74 moles of urea. Then we convert moles urea to grams urea from using the molar mass. So 18.74 moles urea times 1 mole of urea weighs 60 grams. That is going to give us 1124 grams of urea that will form. The last question, how many grams of the excess reagent will remain? As we said, carbon dioxide was determined to be the excess reagent, so we want to know how many grams of carbon dioxide will remain after the reaction is complete. We originally had 25.9 moles of carbon dioxide, but after the reaction is complete, only 18.74 moles of carbon dioxide reacted. That means that if you subtract the amount that reacted from the initial amount that were there, you will get the remaining number of moles of carbon dioxide, which is going to be 7.15 moles of carbon dioxide remaining. And then you can just simply convert moles of carbon dioxide to grams using the molar mass. So 1 mole carbon dioxide weighs 44 grams. The remaining amount of carbon dioxide is going to be 317 grams of carbon dioxide. Another way to do this is basically find out the amount of grams of carbon dioxide that reacted. So you take the number of moles of carbon dioxide that reacted, multiply it times the molar mass to get grams of carbon dioxide that reacted, which is going to be 824 grams of carbon dioxide, and simply subtract that number of grams from the initial number of grams of carbon dioxide. So the excess carbon dioxide is going to equal 1142 grams that we initially had of carbon dioxide minus 824 grams carbon dioxide that reacted after the reaction is complete. That will leave us with 317 grams carbon dioxide in excess.